Hey there, this is Max Doolin. This is the final challenge of the DSA, or Digital Signature Algorithm Series, from the 6th year of the Spokane Cyber Cup. This one, we're going to be learning how to recover the private key when you actually don't know K. In the first challenge, we just digitally signed some information. The second challenge, we knew K, and we used that known K to recover the private key. This time, we don't know K, but we're going to recover K. And then once you recover K, we're going to recover the private key. So I think there's some really interesting lore behind this. Back in the day, the elliptic curve digital signature algorithm, which functionally the math is exactly the same, except that it's just done over elliptic curves instead of whatever normal math is called. And this was working pretty well. They're using digital signatures for their games, so you couldn't run unauthorized games on your console. However, somebody realized that there was a security flaw with it, and using this security flaw, they were able to recover the private key, therefore run any game and pirate games, do whatever you wanted on it. So at the time, this was a big deal, and this was discovered by GeoHot, which was the first person to ever jailbreak an iPhone. So this guy was just on a roll at the time. Now, the bug is fairly subtle. If two signatures use the same K, or the same nonce, you can use some fairly basic algebra to recover the K value. The thing is, if you know K, as we proved in the last challenge, you can also recover the private key. So in the previous one, I actually didn't have the distribution, but I actually have the distribution process here. I actually did it myself, I think, a while ago, to be fair. I probably wrote this challenge 2 or 3 years ago. So here we have S equals K to the negative 1 times message plus AR. And if we have 2 of them, that means that we have this twice. So what you can do is you can do S1 minus S2 and fill this in. And then there are some properties that allow us to cancel things out because we were doing some subtractions. And if we redistribute it, then if the same K value is used, then we are able to completely recover the K value. And if the K is the same, then we can use the signatures to recover K. And that's where this breaks down at. So if we go to this article, it is actually from the same website. It is from the same website. Thank you to the owner of rdistroot.org. Very much appreciate you. Nate Lawson. Thank you, Nate Lawson. You deserve a coffee for this. So it actually explains this process of simplification and canceling stuff out. And then once you know this, then you can just recover you can recover the nonce. Again, if you can recover the nonce, you can recover the keys we did before. So at this point, it just comes all about plugging numbers in. So we have this algorithm both from the solution, but that is also here as well. So just so I have the numbers in front of me, I'm just going to copy this there. And then for the second part of the challenge, with the K recovery, which was in challenge 4 as well, I'm going to copy that. So I also have that when I need it. Cool. So again, we're going to do this in Python. And we're just going to plug in some numbers. So we have we have the same values as before, except now we have sig1 and we have sig2. And that's an important distinction in the case here. So within the sig1, we have the message that we're signing, and then the R and the S values. And we have 2 different signatures. Cool. So it is S1, so 99. 99 minus S2, which is 16. That is going to be the multiplicative inverse of that. So we need to do 99 minus 16 minus 1. And then we're still doing mod Q. So we need to do multiplicative inverse 103. So that's 36. And then we need to multiply that by 500 minus 501, because that is the first message and second message. And then we need to mod that by 103. Cool. So that ends up being 67. So this is our K value. And now we've learned how to redistribute and recover the nonce. We need to do the same thing as before with recovering the private key. This time we recover the K ourselves. So we need to do S, and we can just choose one of these signatures at this point. So I'm just going to choose this signature here, but we just need to make sure they're the same. We needed 2 signatures to recover K. So I'm going to do S, so 99, times K, which we recovered K, so I'm just going to use that variable, minus M, which is going to be 500, and then times the multiplicative inverse of R. And R is there, so that's going to be 75, -1, and again 103, because that is the Q value that we are going to be using here. And then wrap that, and then do 103. So I believe the flag is 101, and if I recall, that is the right answer. Cool. So to recap, cryptography is hard, and there are certain properties of cryptography, in particular algorithms, that if you get wrong, then the whole algorithm blows up in your face. This is why listening to what is secret, what can be known, and what is necessary for the algorithm to work is really important, because these things can break very quickly in very unexpected ways. I think this is a super cool hack. It's amazing. You can just do some algebra and recover the private keys of the PlayStation 3 video games. Some of these hacks seem out of this world. Some of them feel completely insurmountable, especially crypto ones. But this one is fairly approachable to me, so I really want to throw it in here. I hope you really enjoyed this challenge. Crypto is scary, but I hope this was good enough for you guys. Thanks for watching.